everyone. I'm a PhD student from University of Bristol, and I'm happy to present our paper CAMP-VQA, which is recently accepted by WACV. And this model is proposed by a caption-embedding like model perception modeling way for the no reference quality assessment in the scenario of the compressed video. So for our motivation, it's different that the full reference, say with the growth of the user-generated content that in currently on all the platforms like TikTok and YouTube, then that is important to assess the video quality without the reference video. Like we discussed the entire session, like the PSNR or SIIN, that will not work in this scenario. So in that way, that we need to propose certain perspective metrics then like can model in the human perceptual way to predict the video for those scenario. So the UGC videos are very challenging is because they're captured by like different devices. Like we can use our phone or camera, like upload it to all those platforms. So all this video will under like different lighting and capture conditions. And then when they upload it to the platform, it will go into multi-stage of compression and transcoding. So that will create like different type of artifacts or different type of distortion, and which is very diverse. So you may see like blocking or blur or any type of distortion and the temporal distortion as well. And those artifacts normally they mix together. It's not just one type of artifact. And so to tackle this, normally in the perspectral no reference quality way, then follow a certain workflow, like we constructed a sophisticated feature extractors to using certain deep network to extract the features without using any reference. And then we use a regression head to predict the score that we want. So the deep learning based no reference video that made a very good progress. But there's still a bottleneck. When we wanted to train the regression task on those things, we only have MOS. Then the mean opinion score that only provide a single score for this. But it's like a weak supervision if we wanted to let the model to understand what is the quality artifacts way. So which means if we wanted to do like fine-grained detail, then we need to annotate lots of labels on that part, and that is very expensive and is not really scalable for the large data set. So the key challenge for that is how can we like extract like certain semantic features about the quality, but create it like a human-like queue, but without using the manual artifact annotation. And that is the whole idea of our proposed model. So to tackle this, we proposed our CAMP-VQA framework, and we wanted to extract all those features without annotation. So how can we do that without any help from the human? So we can simply, like, if we wanted to extract all those distortion, we only wanted to focus on those distortion areas. So all of the other thing, it will consider the redundant area for us. So to tackle this, we propose the frame difference way. So we calculate the frame difference between the continuous frames. So that way we will get a residual map. The residual map will show how is the motion change, how's the distortion likes, and most highly focused on the changes. But because we calculate those maps, it will create lots of black area, which is highly is not like really important information for us to think about. So to redundant those information, we can do the fragmentation ways. And align with this, we can get two types of fragmentation with align with all the perspectual ways. And then in that way, we can use another way, a VLN, to extract the quality description for us. So that was the whole idea of the proposed model. Our proposed model is by using VLN to automatic to generate the caption from the two key fragments that I mentioned earlier, and then align with the in total captions that align with the human perspective. So by doing this, we need to create like a prompt to guide the VLN to get the caption that we want. It's not like generally describe the video content, but it's the quality related way. So when we create the prompt, then we were thinking like the video will have all this metadata like resolution and bitrate, and then those type of thing is like we wanted to consider in the quality artifact way. So by using different type of metadata from different video, and then extracted the fragmentations that we only focus on the distortion. Along with those two, we can adjust our prompt for every single video, and to guide the VLN to get the like the high level semantic artifact features that we can get. And as I mentioned earlier, that the important part is like we need to build a sophisticated feature instruction. So for this caption, as provided as a semantic features, and we create 3 type of component in our proposed model, which contain with the semantic features extractions, and the spatial temporal information is also important that we extracted it. And combine all this multimodal feature fusion that we already have tons of features that are getting the representation from video. And then we're using a MLP regressor head simply to train it and then regress it to the predicted quality score that we want. So for the detail in the frame difference fragmentation, because the quality degradation is normally very important and occurs in the area with the visual change. So we take 2 frames and then calculate the residual between the interframes, and then divided the entire residual map into a non-overlapping patches. And for each patches, we can calculate the residual intensity for each patches, and then we rank it, and then select the top K patch to form the fragment that we wanted to, which is the only important regions that we wanted to focus on the distortion. So this way we will save some computation resource, and then save some computation times, and only focus on the important region that is matter to us. So this is the module of the diagram of how we get the ranking. So like this is non-overlapping, and then we can see from the cat, then this type, like the middle of the patches is most highly contain lots of information than the rest of the black bit. So we rank the top of the top ranking of the patches, and then we get the fragmentation we want. So for the residual map, we get the selected residual patches, and then align with the original frame, we can get the fragments from the same pixel position, forming as a information from the original context. So according to this quality-related prompts, I will like roughly describe it how we use it, but in the detail of the prompts, we can see you can check our paper to see the detail of the prompt. The whole idea is like in that way, with our key fragments and all this guided prompting, then we don't need to reliance on those costly and fine-grained annotations for each type of distortion. Instead, we use VLN to extract it automatically for us. So that's our key idea. So this is an example for how is the captioning work. So we have the original frame from the video, resize it to extract it like an overall impression for the video, like in quality wise. So like this video, the VLN will give us like certain description in a high level, like serving, blocking the flat areas, and all those fragments will only focus on the distortion we need. So we extracted the artifacts caption by doing this captioning. And by overlapping and duplication and concatenating, we can get in total text description for the video. So because we wanted to map the text information and the visual information in the same latent space. So in this extractor, we use clip as our backbone to extract the text inputs and the sample frames to pass the extractor and then getting into a semantic embeddings in 3 levels, which is the first one is from the original image, and the second two will be from our text embedding. And we apply a global average pooling along with the temporal dimension to get like a video level representation for the video. So in that way, we can align our text generations and the original visual changes from the video, and then align them into the same semantic latent space. And also important for video quality assessment is we need to build a spatial temporal features, which need to be very focused on the spatial temporal distortions. And in that way, we use 2 types of architecture to do so, to get the thing we want. So for the first part, for the spatial information, we use swing transformer to get the features from the frames itself and capture the long range of dependency in the image. And then for temporal motion extractor, we use slow fast as our backbone to do a dual pathway design to getting the general motion patterns from a broader way in the slow path and the fast quick motion change in our higher sample rate in our fast path. So for this type of 3 type subjective video quality, then we can So the subjective video quality is jointly affected by the semantic perception and the spatial temporal information that we wanted to calculate. So we therefore to combine those 3 type of features to apply a regression head on that to regress the score we wanted to use. And here we use the compose loss function by using mean absolute error and the rank loss to ensure our accuracy and the consistency of the ranking. So for the performance comparison, we did our evaluation on 6 mainstream UGC benchmark dataset from the one from the CVD 2014 to the newest one like 5VD. And to this performance test, we did 2 part of experiment on our model. First is the intro dataset experiments. So we train on one dataset and then test on the same dataset. And then the other part is like we train on a large scale UGC video dataset, LSVQ, and then fine tune our model on the target dataset. So see the performance comparison of our model. We are leading of all the dataset and then giving a very consistent performance on everything. And for the specific use case, like we know that's for gaming video, which is focused on more like the motion change and different type of motion artifacts. And then the other one is the short-term video, which is with all the content change very frequently and vary with different content. So we choose 2 type of data set. One is the gaming, and the other one is KVQ to target on different type of use case. So we can see that on those 2 type of data set, we still leading on all this performance. And for real deployment, it's very important for doing cross dataset setting testing as well. So we use our train model on LSVQ to test on target dataset and to test if without fine tuning if our model can still exhibit the strong generalization. And for as detail of the ablation studies, we explore the impact of our generated captions on the video quality scoring through different semantic embeddings of the sample videos. So for 5VD data set that provided like 6 dimension of different type of artifact, then we can test it. So we only use our semantic embedding to test on 6 dimensions to see if it's just because we're adding some actual text information, or is it actually related to the artifact we wanted to use. So like we can see from the data set that here, even with the text embedding itself, it shows a very high correlation with all these artifacts we wanted to guide it to, which means those type of information generated from the VLN is not like randomly, but they actually provide some semantic signal towards guiding the perspective quality prediction. And we also test like different combination of those 3 types of semantic embeddings on 2 data sets. And here we also did another ablation on a content data set. So we asked the, for the content embedding, we asked the VLN to generate something, just describe how is the video's contents like, and then we added it to our embedding ablation test if it's actually the content will help to guiding into the quality prediction. But if you can see from the bottom line, when we adding the content embedding, it actually reduced our performance. Then which means that in quality prediction, the content might not be useful to as a prediction. But with our text generation of quality aware caption, it's showing the best performance here. And according to the quality-related hints, which we extracted automatically from the video metadata, and to incorporating those hints, our prediction is improved. So finally, it will be on the multimodal feature extraction. So we have 3 main components from our architectures. So we test each component, how it contributes itself on the quality prediction. As we can see from the table, the 3 type of features complemented one and another, and that contributed to our robust and quality prediction performance. And I added a figure and showing that on different type of artifacts, how our model predicted. So from 5VD, they virus different type of artifacts. So we can see from our model prediction on each type of dimension, it correlated well. So in conclusion, we propose a novel no reference video quality models that just use VLN to get the artifact annotation without the manual annotations. And our model introduced like the strong, robust caption generation, enable the automatically extraction of the 5-grain quality related caption. And we can use as a substitute to the manual annotations. So the unified multimodal framework integrates the 3 types of components that contributes to our video representations. And our model achieved the state-of-the-art performance and the robust generation. So for future work, because we were thinking about the content information that in the ablation study, is it the way that we can guide our semantic understanding on both type of direction, then we can unify the video question answering and video quality assessment at the same time. Thank you for listening, and I'm happy to take any question now.
Thank you, Xinyi. Any questions for Xinyi? Yes, Alex.
So thank you for the presentation. I think the cross dataset analysis is really important. We see that a lot, right? Is that if you test and train on the same data source, it works well. And as soon as you then abstract that across different data sets, it just falls apart. So I think that robust analysis is really important for production use cases. My question was on the top K selection. It's kind of an interesting design choice. I'm curious how conditional was the performance on the choice of K, and also what would happen if you had, let's say, you had like local motion versus global motion? Because obviously, if you've got kind of global motion, then most of your blocks are going to have the same value. If you've got local motion, then obviously it's going to be a lot more spiky.
So if we can go back to the page that. So for the top K, we currently extracted to targeting to the input model of the next extraction of the feature. So for if the input of a framework is 224 times 224, then our target weight will getting the top K from these resized models. So and the top K is ranked by the residual density. So we rank all these patches, like from here we have maybe like 800 patches. But if our input model from the next level is target into a square size, then we use the calculation that K can equal to P squared divided by the resize size, and that way we can extract the target size we wanted to use. So that is our top K.
Okay, so I assumed it was a parameter that you could kind of tune to kind of trade off performance and kind of cost.
Yes, and we try a different type of deep learning model, and then with different resize size we wanted to use. Of course, the bigger size you wanted to input, of course, it will give you a better prediction and giving you a better feature instructions. But the real time employment, or in the real world scenario, that we need to save the computation time as well. So here we just use the smallest square to get our features, and then it's already like showing good results on that. So it's no need to expand the resize size.
The comment on global motion and local motion, I think it's really important. We haven't explored that, but I mean, my guess is it is a sparse signal. It will be again sparse signal. It will encounter, take into account like a bit of noisy bits. Like if you have like flicker, it will show up there for sure. But it's not the only channel. This is just
of course, yeah.
Yeah.
But obviously, when you do top K, there's always the danger that you're going to miss for features.
Yeah.
And how important those features are probably depends on the content type.
Yeah, we also work under the assumption, because usually you have like you work in high resolutions, so you expect to have a lot of spatial redundancy as well.
Yeah.
That was, but yeah, there could be cases where we miss things for sure.
Any other questions?
So I don't know these data set, and like Alex said, you train in one and test in the other. So my curiosity is that first question: if you train all of these data sets all together, would that ready to use for the general in the real world? That's one first question. And second question is that, okay, you know that I work on underwater or low light, and if I want to fine tune that to fit to my purpose, how much or how large of a data set that I need to fine tune your method to work well with my situation.
So the first question, I will answer the first question first. So you were talking about like we combine all the data set. So yes, currently we are using the largest scale data set on UGC scenario to train our model and test on other smaller target data sets. So that will be our use case.
So if you train everything together, is that ready to use in general?
Yes.
Okay.
So we train our model on this large scale data set, and then you can use just use a single video to do the inference. It will work on our provide train parameters. Yeah.
Okay. And then the second question: so if you want to fine tune, how large of a data set that I need.
So, so for this fine-tune question on other on other scenario like underwater, so I will assume like for other cross data set tests like we did, it will be very similar. So we first to test it on our provide fine-tune model and maybe create another small set like 200 data set and then fine-tune on top of that part, and that will work.
Okay.
That's currently what we're doing.
200. Thank you.
Okay.
Okay. Let's thank Xinyi. Thank you, Xinyi.
Thank you.